All right, guys, here we go. Online astronomy course, something I swore I would never do, but here we are. But we'll press on, we'll make it work. For the past couple of weeks prior to our extended vacation, we talked about how stars are formed and how they live and how they behave as they get elderly. And we saw that star formation is governed by how much mass is involved. Remember, mass equals gravity. We also talked extensively about some of the nuclear processes involved. We talked about hydrogen fusion. We talked about helium fusion. We talked about the triple alpha process. We talked about hydrostatic equilibrium and the main sequence as is delineated on the Hertzsprung-Russell diagram. And so now here we are, we need to talk about the death of stars. Now why do we need to do that? Well, remember what the big picture is, what the finish line is for this course. We're trying to get an understanding of dark matter and dark energy. In order to do that, two critical things have to be in place. We have to have a way to measure distances, and we also have to have a way to measure speeds. Speeds we will cover at a later topic, but we're still on the topic of distances, and we're talking about standard candles. Now the first standard candle we already talked about, a variable star. This is a star that is elderly, that has a varying fusion rate, and that unlocked the door for us, if you will, to see what distances were involved beyond our immediate vicinity of the Milky Way galaxy. But to see even further out there, to measure even further, we need other standard candles. The standard candle that is in play today is something called a Type 1a supernova. This is a star that dies, and we need to understand how this star dies. And back to the original premise, we have to understand how stars in general work. So we're on page 75 in the workbook, and go ahead and hit pause if you need to get to that page. So we're on page 75 in the workbook. The topic is the death of stars. Once again, we're going to reshuffle the deck according to stellar mass. So the first category will be stars that are less than 0.4 solar masses. Those are our old friends, the red dwarfs. The next category are stars that are between 0.4 solar masses and 8 solar masses. Those stars are referred to as low mass stars. And again, for the purposes of evaluating star death. And the third category, stars that are greater than 8 solar masses. Those are high mass stars. So, just by way of review, let's look at red dwarfs for a second. We talked about this last time we met. In a red dwarf, the fusion process is limited to hydrogen. And remember, the magic number, the critical number for hydrogen fusion is 10 million kelvins. Don't forget that, you'll see it again. The fusion process is limited to hydrogen in a red dwarf. And once the hydrogen is used up, fusion stops. The star cools. And recall, we haven't witnessed the demise of a red dwarf yet, simply because the universe hasn't been around long enough for one of these things to die. They have an estimated lifespan in the trillions of years, and we've been around for 13.8 billion years, so we're just getting started. But what the physics tells us is that, recall that a red dwarf is unique in that it is the only star that has a convection process that goes from core to surface. And so this material is constantly being churned. The highly heated, freshly minted helium rises to the surface of the star, the cooler hydrogen goes back down to the core, and it churns and churns and churns until all of the hydrogen has been turned into helium, and now what you wind up with is just a big ball of helium, and that's it. The star is not big enough to exert enough gravitational pressure to trigger helium fusion, which, recall, is at 100 million kelvins. So that's as far as it goes, and it becomes what's called, the term is a black dwarf. So that's the story of a red dwarf. Now, for larger stars, the overview is that the fusion continues and the mass is sufficient to trigger helium fusion. And recall, that's our triple alpha process. Also recall, stars that are less than 2 solar masses, you have core helium flash. Stars greater than 2 solar masses, no core helium flash. And in both cases, the cores are converted to, remember the products of the triple alpha process. The core is converted to carbon and oxygen. So, that takes care of page 75. We'll pause here and go on to the next page.